In this video, we're going to be talking about apparent weight and solving for various elevator problems. So we have 5 different scenarios where we're going to solve for what is the apparent weight of a 70 kilogram person. So in all of these different scenarios, we have different types of acceleration and directions. So the first thing we're going to do is use Newton's second law, which is F net equals mass times acceleration, and I'll put the subscript net next to the A so we know that's the net acceleration. So the net force is the sum of all the forces acting on the object, and the object, or the thing that we're focusing on in all these problems, is the actual person. So for each of these diagrams, we're going to have the force of gravity straight down because of the Earth's pull, and then we're also going to have Fn, the normal force, a force perpendicular to the surface of the floor, pushing up on the person's feet. So what we can do is we can replace this net force with the sum of the forces acting on the person. So I set up our formula as Fn minus Fg equals m times A net. And the reason why I did minus is because forces are a vector. And what I do is anytime I have a force directed upwards, I make it positive. And anytime I have a force downwards, I make that negative. So I have Fn because it's directed upwards minus Fg that's directed downwards. So Fn is our apparent weight. So that's how heavy the person feels, because if the floor is falling away from the person's feet and there's less force on the floor on the person's feet, they're going to feel a little bit lighter. Just like the other way around, where if the elevator is accelerating upwards and pushing against the person's foot harder and harder, then it's going to give them that perception that they feel heavier. And then Fg is the pull that they get from the Earth. That is their actual weight. That value isn't going to change throughout these problems. So what you can do is we can go ahead and plug in an Fg, because we know that it's mass times 9.8 every time. So we know the mass is 70 kilograms, and then the G value is 9.8. Okay, equals mass times A net. The mass is still 70 kilograms, and then the net acceleration is the acceleration that we're going to place in a little bit later before we solve for our Fn. And then we'll just leave this as Fn because that is the apparent weight that we're looking for. So what we're going to do is identify the net force in each of these scenarios so that you can see where to include these different accelerations in this setup over here. So our first one, it says the person is moving at a constant velocity, and constant velocity means there is no change in velocity. So the acceleration for our first scenario is 0 meters per second squared. So in any case that a person is moving at a constant velocity, whether it's slow or fast, up or down, if there's no change in velocity, then the rate of change is 0. So then you would have a net acceleration of 0, and the person's apparent weight is going to be the same as their actual weight. For the second scenario, we have a person speeding up at 2 meters per second squared. Now, because that person is speeding up in the downward direction, you would say that their acceleration is negative 2 meters per second squared, because you have to have the net force directed in the direction of the acceleration. And if it's going faster, then there's going to be a little bit more force going downwards than there is going upwards. For our second scenario, we're speeding up at 3 meters per second squared. In this scenario, we're going to need more force directed upwards, so our net force is directed up, and our net acceleration is going to be positive 3 meters per second squared. For our fourth scenario, it slows down at 3.5 meters per second squared. So this scenario is the first one that's a little bit tricky because the sign of the acceleration is going to be a little bit different than the direction that the person is going. So typically when people see that something is going downwards, they're going to think of a negative, but it slows down as it's going down. So if something is falling downwards and it's slowing down, that means the force has to be directed in the opposite direction in which it's moving. So if it's moving down but slowing down, that means there's more force directed in the upwards direction. So if the net force is directed upwards, then so is our acceleration, and our acceleration is positive 3.5 meters per second squared. Or the other way to think about it is if it has a negative velocity and you add a positive 3.5 meters per second every second, it's going to make that negative velocity increasingly smaller, hence slowing it down. Okay, this last one is pretty similar. It's slowing down at 4 meters per second squared, but it's moving upwards. So if it's moving upwards, but it's slowing down, that means the net force is directed downwards. So the acceleration is going to be negative 4 meters per second squared. Okay, because that net force is directed down to slow something down that is moving upwards. So then that net acceleration is also going to be negative. Okay, so it's all about reading carefully with the details, whether it has any kind of acceleration at all. And then if it does have a specific acceleration, do you need to include a negative sign or not? Now, the net acceleration is what is actually happening in each of the scenarios. So after you figure out what the net acceleration is, then you just have to plug it in right over here and then work out the algebra from there. So say, for example, we were working out this scenario over here, speeding up at 2 meters per second squared. All we would do is we would set up Fn, subtract 70 times 9.8, and then set that equal to 70 times negative 2. And then we would have Fn minus 686 equal to negative 140. Add 686 to both sides, and then we get our final answer of 546 newtons. Okay, all of the rest of the problems would be pretty similar, except you would just have a different net acceleration value. So if you're working on this problem, you'd place the negative 4 there. For this one, you'd put the 3.5 there, and then so on. And what I typically do is I double check my final answer by comparing it to the actual weight. So I know if something is speeding up downwards and then the floor is falling away from my feet, it's going to be applying less force upwards against my feet. So therefore I should feel lighter. Now, normally my FG is 70 times 9.8. Remember, that's our actual weight. So we would normally feel like we're 686 newtons if we're standing at rest or moving at constant velocity. And now we feel like we're 546, which is less than our actual weight. So that does match up with the idea of feeling lighter. So that would seem to be correct. So to sum things up, we're going to set up Fnet equal to MA. And then with our different elevator problems, our Fnet type formula is going to look like this, Fn minus Fg. Our Fg is going to be pretty consistent because that's our actual weight. So we're going to take our mass times our 9.8. Our Fn is our unknown variable that we're solving for. That's how heavy we feel. And then on the right side over here, we have our M and our A. The mass is still the 70 kilograms, the number we're given in the problem. We're just going to have to make sure we correctly identify our net acceleration in each of the scenarios and then plug that in here, do a little bit of algebra, and then solve for our normal force for our apparent or perceived weight. I hope that was helpful in helping you understand apparent weight and elevator problems. Thank you for watching and listening.